after.
The cloud.
And you record to the cloud as a backup.
There we go.
Lovely.
Hello,
Okay. Yeah, so I took the airplane out yesterday.
Which one? Yours?
Mine, yeah.
Oh,
Because we were going to fly it to get repaired.
to Indianapolis.
We were going to fly it to Indianapolis. The weather was kind of crummy for a long distance flight like that.
Mhm.
And I hadn't had a chance to actually debug the thing at all because, Mom and I just bailed out, and
Right.
flew to
Never mind.
Austin, and then, crazy week after that. So this is my first chance to get back into it.
Mhm.
Worked fine. So then I started flying it around the pattern because I thought, well, maybe it has to warm up a little bit, or maybe some vibration or something. Worked fine. So I talked to the guy, at Skill over there, and he said, well, if you submit it for repair
Mhm.
under warranty
Mhm.
and they find out there's nothing wrong, they charge you.
Oh,
It's like, what?
okay.
So not only do they charge you for that, but they won't even consider a repair until they've upgraded it to the top level mod, which they also charge you for. So now I'm looking at sending the airplane away for several weeks and getting several $1,000s of charges, even though it's under warranty,
Mhm.
plus possibly a penalty charge if they don't find anything wrong.
Oh my.
So now I'm thinking, okay, I got this airplane that's just a little flaky.
Mhm.
I don't want to fly it in real bad conditions. Like I don't want to do any IFR flying because if it craps out again, I'm going to be in a little bit of trouble.
Mhm.
Not that much trouble, but a little bit of trouble.
Mhm.
So now I'm thinking, okay, I'm just going to do some standard VFR flights,
Mhm.
real simple flights that aren't risky at all. And if it craps out during that period, it won't matter.
Mhm.
And if I can get it to fail, and I can take a video of it failing, and then I can send that in, and I won't have this problem.
Okay.
So that's what I
That's a
think
better idea.
the strategy is going to be. But
What a pain that it did that.
yeah, well, it's 15-year-old electronics, and
Huh.
things are going to go wrong with it. It's just, Avidyne says, well, if there's nothing wrong with it, we're going to charge you under warranty. It's like, what? So, okay.
Wow.
They just want people to be very deliberate about things.
Mhm.
Okay, well, that's
Wow.
that's the scoop there. So I will be flying around.
Oh, well, that's good. Maybe you should just always fly toward Indianapolis. No, if it does do it, then you just take it the rest of the way, drop it off. and borrow
Yeah,
it
well,
and
it's
bring
yeah.
it.
All I need it is for it to fail again, and I can take a video of it, and then it's off to repair.
Mm. Wow. Well, I guess it's good that it's working, except that it wasn't working, and so
Well, yeah,
you
just-
don't really trust it.
It went through that one failure, and
Mhm.
could have been a little piece of dust in the contacts.
Mm.
Just that would have done it
Wow.
and cleared away, or maybe a little humidity or something.
Wow. Finicky.
Well, concerning. Just like
Yeah. Yeah, you're kidding.
it's like I just got that radio repaired.
Now this. Yeah.
Oh well. Oh, it's 10. It's one. It's after time.
Oh my. Yeah. All right. Well, you've got 6 people here, and the rest of people.
Oh, yeah.
come a couple
Yeah.
minutes late.
Couple more to come in. Oh, you don't want to miss this one. Yikes. This is the climax of the show here. We're going to talk about test design and clean tests. Should be a good one.
Yeah. All right. Well, I'll jump on afterwards, so you can go ahead and get started.
All right. No announcements or anything?
No, not right now. I'll make them later.
Okay. Don't want to do another tour of the. We did that. Why did we do that? Because
we lost the internet. And
Yeah.
then it was converting the video.
yeah. Oh,
And
that's
the
right. We had an internet dropout.
Yeah.
I've been getting more and more of them at the house.
That's what Mom said.
Yeah, it's starting to get unusable. Have you been noticing, like the camera will tell you if the internet goes out?
Yeah, unstable.
Yeah. Have you been noticing that here?
Yeah, last week I dropped out. Remember, I dropped out, but you didn't.
Oh, yeah.
Mhm.
Okay. Have you seen any more of these unstable reports over the last few days from the office here?
No,
Okay.
no, I haven't.
Huh?
I haven't been here.
No, but the camera should have said something.
Oh.
Right, the security
No,
camera.
I don't know. I don't know.
It should
I'll go
say,
back and
oh,
look through
out.
the-
Oop,
Yeah, I haven't gotten notices.
Okay, all right. All right, guys, let's go. Let's see, we got 8 folks in. We're gonna head out. Let's do this. We're gonna begin with clean tests. Let's see if I can figure out how to share my screen here. Share, oh, there's an interesting share screen options. I wonder what that is. Who can share? Oh yeah, okay, I get that. All right. Yeah, stop it, stop it, stop it. Okay, who got muted? You got muted.
Yeah, I'm muted.
You're muted. Okay, good. All right, so I'm going to share my screen. Share screen, and the screen I'm going to share is that one. Come on, come on, come on. Give me the button. Give me the button. There it is. Good. And everybody should now see clean tests. Lovely. Okay. So we're going to start today's lecture with just a walkthrough of what tests should not look like and what tests should look like, just from a basic cleanliness point of view. And in the midst of this lecture, I'm going to be talking about some of the principles of test cleanliness. So I'm going to show you a test that I wrote, gosh, 2007, I think it was when I wrote this test. And I was working on a project inside of fitness. Fitness is the acceptance testing framework that my son Micah and I wrote 20 years ago. You know, we've been maintaining it ever since. A bunch of people work on it now. And sometime around 2007, I think it was, I was adding a new feature to fitness, and I was testing that feature. And I wrote this test. And it worked. The test works. It's, you know, and, you know, it was, you know, part of the test suite that we ran all the time. And then many years later, probably around 2015 or 14, I was goofing around inside fitness again, doing something else. I don't know what it was. And I happened to run into this test, and I thought, holy cow, who wrote this? You know that experience, I'm sure. So this test has a number of significant problems to it. Now, the title of the slide says, what does this test do? I'm not going to even push on that. You don't need to know what this stuff does. I'm just going to walk through some of the things that I find very annoying about this particular test. So we begin. The test has more than one logical assert. Now, there is a rule in test-driven development called the single assert rule. The single assert rule says that a test should only assert one thing. People get this confused a lot. They tend to believe that that means that the test should have one assertion statement, but that's not correct. A test can have several assertion statements, so long as those assertion statements are asserting one logical thing. You may have a logical thing that has several different components to it. You can assert all of those components, and it is still one logical assertion. I can make this clearer by defining how tests are written. There's another rule or another pattern in test-driven development, or just in testing in general, which is called the AAA rule. The AAA rule says that all tests are composed of three elements: arrange, act, assert. The arrange part arranges the data, arranges the state of the system so that you can then act upon it. The act is the thing you're testing. So the second part of the test is to do the action that you are testing. And then the third part of the test is to assert the outcome of the action. So arrange, act, assert. That's the typical pattern that virtually all tests follow. The single assert rule really should be called the single act rule, because what we're really trying to get at there is that we don't want tests that are written like this: arrange, act, assert, act, assert, act, assert. We don't want multiple actions. We don't want a chain of dependent actions going on inside the test. What we want instead is a single action and then a single logical assertion of that action, and then you're out of the test. This test that I've got on the screen does two actions. You can see them there. There's this get results for page contents and get table. There's several things going on in there. Actually, the assertion, the arrange part, the arrangement actually arranges two things. There's two actions, and then there's a set of assertions. You can see there's 5 assertions in there, but some of them assert one action and some of them assert the other action. So this is a terrible violation of the single assert rule. It should be divided up into 2 tests. The next problem I have with this test is that there's a lot of what I like to call accidental complexity. And I highlighted all this accidental complexity in yellow. Actually, there's more accidental complexity than that, but I highlighted the worst of it all in yellow. And the one thing you might see right away are all those unescapes. Now what's going on there? This test actually gets an HTML response back and then decodes the HTML to see what's going on, see what happened during the actions. And of course, the HTML stuff has all that ampersand LT semicolon and ampersand GT semicolon for the special characters. So I need to unescape them so that I can see the special characters in the strings. And you can see the strings there. I've got less than signs and greater than signs and dollar signs and things like that. And of course, you know, in HTML, that's all going to get escaped with the horrible prefixes that they use. So I have to unescape it all. And you can see those unescapes are everywhere. That's just noise. The test really shouldn't be worried about having to do that. It's accidental complexity front and center in the test. There's a bunch of magic numbers in there, 1s and 2s, 0s and 3s, 1s and 3, 1 and 4, 1 and 5. Those are all just magic numbers that the poor person reading the test really has no idea, you know, what those mean. If you dug into the test long enough and figured out what the test was actually doing, you would probably understand why those numbers are there. But if you're just in here for a cursory look at this test, those numbers are completely befuddling. So that's more accidental complexity. And then you've got this table scanner and get table stuff, and that just looks completely out of place somehow. So overall, there's a lot of this crufty, nasty, noisy, accidental complexity that obscures the intent of the test. The next thing to note is that this test runs very slowly. If you look down at the bottom, you'll see that highlighted in yellow. It's taking 1.3 seconds. 1.3 seconds for a single test. Now that violates so many rules. It's kind of hard to exaggerate just how bad that is. Why is it so slow? Well, it's slow because of some of the other problems that I'm going to show you. But the short answer is that this test actually starts up a separate JVM and executes half the code in that separate JVM. And of course, starting up a separate JVM takes a fair bit of time. So that's one of the reasons, although I'll get into more of the details of that in just a minute. And those details are this. This test executes over a very wide scope. I've got a little diagram down there at the bottom. You can see where the test is. The test is against the wiki page and the test responder. You see those arrows down there? Okay, so they exist in one JVM, but the test is actually testing something that happens in Slim. Slim runs in a completely separate JVM, and the test responder communicates with Slim over a socket. So there's a socket communication in here and an entirely separate JVM and an entirely separate process startup. And I'm testing the operation of this very remote thing through a a very far away responder. It's the best way I could say it. The scope of the test is far too wide. It's always a bad idea to do that. Now there are times when you do integration tests, and integration tests by definition have wider scopes. But this was not an integration test. This was a unit test. I was trying to test two very particular behaviors of SLIM. And I decided to do it through a socket. I don't know what was the matter with me that day. Maybe I was tired or something. You know, sometimes you just aren't really in the mood to program, but you got to do it anyway. And then you make a mess. And by the way, the best advice there is don't program when you're tired. Don't program when you can't focus. Go find some way to get your focus back before you write any code. The next thing I'd complain about are all the names that I used. These are all colloquial names: Bob, Bill, John. They have no meaning at all to the person reading the test. You know, why Bob? Why in the world is Bill in there? There's no justification for those names. There's no explanation for what's going on there. The names just appear as, you know, random guys. So that's bad too. When you are writing tests, you want everything possible to explain what's going on. Those names could have been explanatory. I could have been explaining in those names what I was testing. So this is where these tests ended up. I actually refactored them into these two tests. And the first thing you'll notice is that there are, in fact, two tests, right? So there were two things I was checking. And the second thing you'll notice is each of those tests is 2 lines long. That's nice. You know, the person reading that test is not intimidated by the test. They look at the 2 lines and they say, oh, okay, fine. And what are we testing? Well, we're testing that the matched symbol is replaced. Well, gosh, what's the symbol? The symbol is S. What's the value? The value is value. Notice I'm not using Bob and Jim. Those names are actually meaningful. And then I assert the expectation that if I use the symbol expression syntax $S, then I will get the value out. And in fact, I'll get a little message saying that pass $S is value. Now, you don't need to understand an awful lot of that. Just you can kind of look at that and grasp the notion that, yes, the symbol S does appear to be replaced with the token value, which is nice. And then mismatched symbol is replaced. And you can, well, I'll let you analyze that test for yourself if you want to. But again, these tests are much better than the previous ones. There's one logical assertion per test. I put down here that there's no accidental complexity. That's probably not perfectly true. There's all those square brackets and stuff. Probably didn't need all that in there, but the accidental complexity is vastly reduced. The test is very fast. Notice the timing on it. It's 1/4 of a second. That is just the JVM startup time of the testing system. So the test actually runs in microseconds. And how did I get it to run in microseconds? Well, I didn't run it through the remote responder. I ran it in SLIM. I figured out a clever way to avoid starting up SLIM in a foreign process and communicating through a socket. I found a little clever way to short circuit that so that the test responder actually stays in process with SLIM. And I would set that up for testing purposes. In normal production, SLIM will always run in a separate JVM, always communicate through a socket. But in a testing environment, there's no need for that. And I could vastly speed it up by short circuiting that. The code that does the short circuiting exists in the production code, but it only gets activated during a test. And you might think, well, that's ugly. You've got code in the production environment that only gets activated during a test. And then my response to that is, yeah, but it shortened the test time by a full second. Yeah, I'm not gonna complain about that. It was the right thing to do. And of course, the last bullet item down there is that I'm using meaningful names, right? So instead of Bob and Bill and John, I've got value and wrong value. I suppose you could argue that S should be the word symbol, although, I think S is probably self-explanatory. So, okay, these tests may not be perfect, but these tests are much better than the previous tests. Now, here's the ugly part of that. What you saw me do, I'm going to back up the slide again. You notice that the function I'm calling here is called assert expectation message. Now, this is called a composed assertion. I'm not using one of the standard assertions that comes with JUnit. I've built my own assertion function, and that's called a composed assertion. I have composed my own assertion function. If you look in that function, you'll see all that accidental detail stuff. Well, not all of it. A lot of the accidental detail stuff is still there. The slim table stuff, the table scanner stuff, that's all still there. The magic numbers are vastly reduced, but some of them are still there. You can see that there's some complexity there. And that's okay, because that complexity is hidden. It does, that complexity does not get, you don't get slapped in the face with that. When you read the tests, you can kind of get the idea of the tests without having to go into this level of detail. If you want to go into this level of detail, you can, and that's why that's there. This is a common strategy when you're writing tests. Get all the gunky, horrible stuff you have to do, put it in a composed assertion, and then let the tests just call the composed assertion, which has a nice name and allows people to live in a fantasy world where the complexity is hidden from them, unless they absolutely need to see it. So one of the strategies to make your test more readable is to compose your assertions, write your own assertion functions so that complexity is hidden and your readers will thank you. Here's another technique that I use, which is called a composed test result. Now, what was going on here is this was an exercise that I had people doing for a long time. If I'm teaching a test-driven development course, I have people go through a bunch of exercises. I haven't been able to do that with you guys because this is a very compressed testing course. Typically, I teach test-driven development over 2 days, and there's a lot of exercises in that 2-day period. And one of the exercises that I tend to give people is the environment controller. An environment controller is a simple problem. You are going to control a furnace and an air conditioner and a fan, and it might have some alarms. And your goal is to keep the room at a certain temperature within, 5 degrees or 3 degrees or something like that. And there's a bunch of rules about, when you can turn the heater on and how long you have to leave the fan on, stuff like that. So there's some very interesting, complicating rules. And of course, I don't give you a furnace and an air conditioner, so you have to mock those things out. So it's a nice exercise for learning how to mock things. And it's also a nice exercise for this reason. If you look at the bottom listing there, you'll see that there are 5 Booleans. These are the Booleans that describe the outcome of a controlling operation. Is the heater on? Is the blower on? Is the cooler on? Is the high temp alarm on? Is the low temp alarm on? There's 5 Booleans that describe the state of the environment controller. To test that, you can understand that you might need 5 different assertions in every test. And this problem typically had like 14 to 20 tests or something like that. So the tests would all be composed of these 5 Boolean assertions: assert true, assert false, assert true. And as you read through that, your eyes would blur and your brain would kind of turn off because these 5 assertions repeated 20 times, once in each of the tests. And it was hard to see the false versus the true. Code is a really rife environment for optical illusions. And these tests were perfect optical illusions. It's very difficult to read them. My solution to that was to compose the test result. And you can see how I did that here. I actually composed a string of 5 characters. Those 5 characters represented the 5 Booleans, and they would be uppercase for a Boolean that was true and lowercase for a Boolean that was false, which means that, first of all, you could reduce each test to a single assertion, which just asserted that string. And second of all, the reader could look at it and know exactly what's going on, right? So the one test you're seeing up there in that top listing, the heater and the blower are on, the cooler's off, the high and low alarms are off, right? Real easy to see that. So that's another technique that you want to keep in the back of your mind for making your tests readable, keeping your test results composed out of something easily readable rather than 4 or 5 horrible assertion statements all stacked up together. Now, I've already talked about stubbing and mocking. We did all of that last week, so I'm not going to go on to that. And I also talked about first, the algorithm for keeping your tests fast and independent, and so all these other things in first. Let's see, what are they? Yeah. Oh yeah, repeatable, self-verifying, and timely. It's ironic, isn't it, that the reason to have an acronym is so that you can remember what the words are, but I actually have to go to the definition to remember what the words are. And I think I talked about this last time, where we were making things faster by using mocks to mock out databases and mock out GUIs and mock out sockets and mock out hardware. And that's one way to keep things going very, very fast. And yes, we did get to this final result, which was the real meaning of the word first. I talked about that last time as well. The tests come first in everything. They're written first, they're refactored first, they're maintained first. The tests come first because if you don't have the tests, the production code is going to rot. And so the tests are often considered the more important part of the system. All right, so now we're going to talk about, let's see, I've got test patterns in here. Let's talk about test patterns, not test design yet. I know, you want to get to test design. But before we do that, there's a couple of patterns that are very frequently used in test-driven development. There's quite a few of them actually, but there are 3 that I think we should cover here. If you want to know about more of these patterns, there's a wonderful book that was written by Gerard Metsaros. I'll put the name of it in the chat. Let's see if I can get the, yeah, there we go. I'll put the name of it in the chat, and the name of it is XUnit, spell it right, Bob, XUnit Patterns by Gerard Metsaros. There we go. XUnit Patterns by Gerard Metsaros. And that's a book, it's kind of an encyclopedia of design patterns and writing patterns, authoring patterns for tests. It's a big book. It's got lots of really good information in it. And in fact, that whole discussion we had last week over mocking, that came out of that book as well. So good book. Get that book for patterns. The 3 patterns that we're going to be talking about here begin with test-specific subclass. Now imagine that I've got an X-ray machine that I'm writing tests for. And one of the methods in the X-ray machine is the turn on method. And while we're testing, we really don't want to turn on the X-ray machine. Now you can replace this with any dangerous method, you know, like a method that deletes all the rows in the database, or something like that, any dangerous method, or any method that you simply don't want executed in the context of a test. You know, like, for example, communicating over a socket to a separate JVM. They might not want to do that. So one of the strategies that we will use for that is this idea of a test-specific subclass. Notice that I've got safe X-ray for test down there, deriving from the X-ray machine, and it overrides turn on to do nothing. That's the most trivial case for a test-specific subclass. It just overrides the dangerous method to do nothing at all. And then when we test the X-ray machine, we can test functions that call turn on, but the X-ray machine won't in fact get turned on. That's nice, right? It's a little safe. And of course, you could use a spy for this. You could actually put the spy in the test-specific subclass. You could set a little Boolean, and then the X-ray test class could query that little Boolean. So not only would it be a spy, but it would be a heavily implemented spy, because the spy, that safe X-ray for test, would be a spy, but it would have all the implementation of X-ray machine in it, except for the turn on method. So it's kind of a hybrid system being tested that spies on itself, which is kind of clever. That's kind of nice. So I certainly have used test-specific subclasses in the remote past. It's been a while since I've used one, but okay. It is a common enough thing to do. The next pattern I want to talk about is the self-shunt. Michael Feathers came up with this many, many years ago. And it's one of those cases where you want to create a stub or a spy, but you don't want to invest an extra whole hierarchy in it. So look at what this does. This is a little bit clever. I've got the authenticator there. Remember the authenticator from last week, right? Okay, I've got the authenticator there. That's the interface. Look what's implementing it. What's implementing it is the test class, not some separate stub, not some separate spy, but the test class itself, the class that contains all the test methods. And obviously, if you did that, you could build in a stub or a spy into it, and all of the test methods would see all of that stubby, spy-y stuff in scope. Now, this is nice. It's very handy. It's useful if you're going to have a single spy or a single stub. You're not going to have lots of tests with or lots of other stubs and spies. You're just going to have one stub or one spy, and you can mix it in with the tests. It's a little convenient, helps you avoid writing an extra class. Might be a little bit confusing for the reader, not too bad though. So I've certainly used this in the past when I wanted to short circuit the process of actually building an independent stub or spy. It's a nice way to kind of sidestep that problem by deriving from the mocked out interface, deriving the test from the mocked out interface. The last of the patterns I thought would be good to talk about was humble object. And this one is going to take a little bit of time. It's a little more complicated than the others. And let me back up a little bit. Test-driven development is a wonderful discipline. It works in 95% of the application that you are writing. But there is code in every application that you just can't test, or it's impractical to test. So for example, everyone raises this example, the GUI. How do you test the GUI? Well, okay, in the end, testing the GUI represents an awful lot of challenges, because to properly test the GUI, you would have to set up a camera looking at the screen, and you'd have to interpret the bits that the camera sees to determine whether or not the right things were being drawn on the screen. And, you know, nobody's going to do that. That's just impractical, right? So there is this moment in every application where you leave the world of the computer, you leave the memory of the computer, and you begin to affect something in the outside world. And that's almost always impossible to test, or so impractical to test that nobody wants to do it. So what's the strategy then? How do we deal with this code that is not going to be tested. For all intents and purposes, it's not going to be automatically tested. It will be tested manually, obviously. You're going to use your eyes to look at the GUI. But testing by eye is not very reliable. So what do we do about this code? And the answer is this. We extract from that code. You can see on the diagram here, I drew the physical boundary. The physical boundary is right when you leave the computer and you start talking to an outside device, a device that is not in the computer's memory, right? So you divide the code that talks across that physical boundary into two elements. One here I've called the data formatter, the other I've called the driver. And the goal here is to get all of the intelligence out of the driver. You want that driver to be so stupid, so humiliated. That's why we call it the humble object pattern. So humiliated that it's not even worth testing. You know, it should be almost nothing more than a bunch of dumb assignment statements moving data from one place to another. Now, the diagram you're looking at shows the data formatter and the driver. In a GUI, that driver would be called the GUI and the data formatter might be called a presenter. And in that instantiation, this is often called the model view presenter pattern. But the generalization of that is the humble object pattern. Notice the data structure that you see that is used to communicate between the data formatter and the driver. So let me explain that. In the diagram, we go all the way back to the application. The application wants to send some data across the physical boundary to the device. Might be a GUI, might be a database, might be some robot arm controller, doesn't matter. The application wants to send that data across the physical boundary. It enters the data formatter, and the job of the data formatter is to do all of the intelligent work to get the data ready to cross the physical boundary. Generally speaking, the application doesn't really know much about the physical boundary, doesn't know the format of things that on the other side. The application on the left there likes to talk about data that's in application format. The data formatter puts that data into the physical device format, or as close to that as it can get. And it puts it in that data structure down there. So the whole job of the data formatter is to load that data structure down there with data that the driver can push across the physical boundary with a minimum amount of intelligence. We don't want any intelligence in the driver. The data formatter can be tested. That's why I show that test down there. The data formatter can hand application formatted data to the data formatter and then look in the data structure to make sure that it got properly formatted for the driver. And by doing that, we solve the bulk of the problem. We can test the most difficult part of getting data across that physical boundary. The last little bit, the driver, is just too stupid to test, and it's impractical to test. Now, let's give a more physical example. I want to get a dialog box up on the GUI. This dialog box has a grid of numbers in it. Those numbers can be positive or negative. Negative numbers should be written in red. Positive numbers should be written in black. The numbers have 2 decimal places of significance, so they should be rounded and trimmed and rounded to 2 decimal places. The dialog box has a couple of buttons on it. Those buttons have names that depend on the state of the data grid. So in one state, it might be the word cancel. In another state, it might be the word submit. There are other states of the grid where that button is completely grayed out. You can't hit it at all. You can't click on it at all. There's a menu on the dialog box. That menu has a number of menu items, and depending on the state of the system, some of those menu items will be gray or not gray. The application hands the data grid and the state of the system to the data formatter. In this case, we should probably call it the presenter, because if we're in a GUI environment, the data formatter is usually called a presenter. The job of the data formatter, the job of the presenter now, is to reorganize that data so that the driver can pump it across the physical boundary, which in this case means the driver is going to convert it to HTML. The data formatter is not going to convert it to HTML. The driver will. The job of the data formatter is going to be to take all of the numbers in the grid and whatever mechanism it needs to access those data members in the grid, it will use that mechanism to produce in the data structure that will get sent to the driver a simple table of strings. Those strings will represent the numbers properly rounded. There will also be a table of Booleans. The Booleans will represent whether the numbers should be black or red. So the strings will not have negative signs in front of them, right? The data formatter will take the absolute value of the numbers, trim them to the proper size, convert them to strings, convert them to ASCII strings, and then put them in the data structure, and then also load the grid of Booleans with the proper trues or falses, depending on whether the numbers should be drawn in red or black. The data formatter will also load into the data structure the appropriate name for the button and a Boolean to determine whether the button should be drawn gray or not. And likewise, the data formatter will construct all the names for the menu items in the menu and also construct a table of Booleans that will tell us which of the menu items should be gray or not. Now, it should be clear to you that that data structure can be tested by the test without actually pushing the data across the physical boundary. When we're doing the test, we don't let the data go all the way out to the GUI. We hand the data formatter the application data, then we inspect the data structure. It should also be very clear to you that the driver's job is trivial. All it has to do is construct HTML with the appropriate strings in it. Presumably you're using some tool like Velocity or God help you, ASP or something like that, so that the job of inserting those strings into the HTML is not even worth testing. And of course, it will get tested by naked eye eventually. Right? So that is the humble object pattern. The strategy is to pull all the intelligence away from the driver so that the driver is left so humiliated that it's not worth testing. And this pattern can be used anytime you are next to a physical boundary. Now, being next to a physical boundary is one of the times that test-driven development breaks down. You just can't write the test for that driver. There's no practical way to write the test for the driver. So you can't follow the 3 laws when you're writing that driver. There are other times when you cannot practically do test-driven development. A simple example of that would be CSS, right? Most of the time, we do not know what the values are that we're going to stick in the CSS file because we haven't seen it. And so what we have to do is look at it on the screen and then say, no, I want that font size a little bigger. You know, I want that color to be a little different. I want that string moved to the right a few pixels. You know, we're constantly fiddling around in the CSS. And the reason that that's not testable, because, you know, CSS, you could test CSS, right? You could inspect the the strings that you're loading into CSS. But the reason that that's not practical is that at the time you're writing the test, you don't know what the answer is. You don't know what the font size is. You don't know what the position of the string is. You don't know those things. You've got to look by eye. You have to use your eyes to determine that. So another case where test-driven development sort of breaks down is when you just don't know the answer.
My apologies.
Yes, you should apologize. Now, there are other times when you don't know the answer. So for example, let's say that you're working for NASA, right? And you are doing a finite element analysis across the surface of a new airplane wing. You know, you're trying to figure out the best possible shape for an airplane wing. So you've broken that airplane wing up into little tiny triangles, and you've tessellated the surface of the airplane wing with all those little tiny triangles, and the little tiny triangles accept inputs as flows of air, right? Flows of air come into the triangle and flows of air go out of the triangle, and you're going to model the flow of air over that airplane wing to determine how efficient it is. And the purpose for writing the program is to determine the best shape of an airplane wing. Well, you don't know the answer. The reason you're writing the program is to get the answer. So you can't write that test. You can't write the test that says the best answer is this shape, because you don't know that shape. That's an example of where test-driven development can break down, in those cases where you don't know the answer. However, it's also an example of the strategy for using test-driven development to derive the answer. Because although you may not know the best shape of that airplane wing, you do know how all those little triangles ought to behave. You do know, you can predict the input airflows, you can predict the output airflows from the input airflows in isolation from one another, right? So you can write tests for the finite element analysis code, and then you can use that finite element analysis code to test certain airplane wings, right? So once again, those are cases where TDD starts to break down. People often ask me, well, aren't there applications in which test-driven development is not applicable? And the answer to that is no, there really aren't any. You can always write tests for the detailed part of your code. You can always write tests for those, and it's always valuable to do so. There are no particular application domains in which one should not do test-driven development. There are rather areas within every application in which test-driven development starts to break down. Let's see, one more thing, and then we're going to do a break, and this is test conventions. Oh, by the way, remember, put your questions in the Q&A widget. Type your questions in the Q&A widget if you have questions. Put them in the Q&A widget, and I will answer those questions either before or after the break, depending on how many questions there are in there. So last thing we're going to cover this hour is test conventions. How do you name a test? There have been a number of different strategies that people have posed for naming tests. My favorite is the when-then convention, which you notice that that's similar to given, when, then. I don't use the 3-component names, though. I just use the when-then convention, which tells you, it's maybe I should call it the given-then convention, because the first part of the name describes the arrangement, and the second part of the name describes the assertion. And the arrangement also includes the action. So the first part of the name is the arrange act, and the second part of the name is the assertion. So an unbound symbol is not replaced. A bound symbol is replaced. A null buffer does no action. A null symbol does no action, right? These are simple kinds of names that I prefer. This is the mode that I prefer. So I use that kind of naming strategy most of the time when I'm writing code. Here's a bunch of questions that people ask. This is part of the testing conventions lecture here. What do you do about testing private or protected methods? People ask this all the time. And the first answer is I don't test private or protected methods because I can test them through the public interface. It would be very bizarre if there was some code in a private method that you could not reach through the public interface. So I will use the public interface to test my private methods. Principle number 2. Well, what if you really just have to test the private method? Maybe you've got some legacy code or something, and the legacy code is really ugly, and the only good way to test something is to test a private method. Okay, principle number 2 is testing trumps privacy. If you have a private method and you absolutely must write a test for it, then you should relax the encapsulation on that private method. You should make it protected or package scope. You may even have to make it public. Again, testing wins all of these battles. Right? You're not going to not write the test just because the function should be private. In reality, what you should do, however, is ask yourself, why am I testing this private function? Maybe there's some way I can make it really public, for example, by extracting it into another class where it really ought to be public. So that, try that. Because principle number 3 is that testing privates implies some kind of design error. If you really have to test a private method, there's probably some design flaw that's driving you in that direction. So that is my answer to private methods, testing private methods. Lastly, there's this idea of hierarchical tests. Now, if you're a Ruby programmer, you already know about hierarchical tests. If you're a Clojure programmer, you already know about hierarchical tests, maybe, depending on the testing framework you use. .NET people, maybe you do or maybe you don't, although your tools have been able to do hierarchical tests for some time. And if you're a JUnit Java programmer using JUnit, you have not been able to do hierarchical tests for a very long time unless you used the hierarchical context runner plugin. And this has finally gotten built into the last release of JUnit. So from now on, you can do hierarchical testing. What the devil is hierarchical testing? Okay, I probably should have answered that question first, but okay. You may have noticed that if you've got 20 or 30 or 40 tests in a test class, your setups start to get big and unwieldy. So do your teardowns maybe, but mostly the setups, right? And the reason that they get unwieldy is that every test needs its own particular bit of setup, and the setup function accumulates all those setups. So the setup function is additive. So there's a whole bunch of code in the setup that does not apply to the current test being run. It's just there to set things up for some other test that is not being run at this particular moment. As you are running the third test in the class, there's code in that setup that will be executed, but it didn't need to be executed for the third test because it was really only needed for the fourth test, right? So the setups get big and unwieldy because they accumulate all the setups for all the tests. Well, that, by the way, that happens on steroids if you're using some kind of mocking framework, right? Because then you've got to set up all the mocks. That's awful. And then you've got dots and parentheses everywhere. And anyway, a hierarchical test allows you to build a main test class that has inner test classes within it. That's how you do it in .NET, by the way. You just use an inner class. In Java, that's the way you do it now too. But you'll have to look at the instructions for JUnit. In any case, it makes it very simple. Your main test class will have some test methods, and it'll have a setup and a teardown. You can see that on the diagram here. But then your inner test class, which here I called subtest 1, will also have setups and teardowns and some test methods. And another inner class called subtest 2 will have setups and teardowns and some test methods. And now I've got a sub-subtest in there, which is yet another inner class, nested now 3 deep with its own setups and teardowns and tests. And here's how this executes. Let us say that we are about to execute the second test in subtest 2. Right? So it's the second test in subtest 2. What will be the procedure? And the procedure, oh, devil. Okay, that was my phone, and I tried to stop it, and it jumped over to my laptop. Dumb thing. Okay, we're about to execute the second test in subtest 2, and this will be the procedure used by generally all of the test runners that I've mentioned. First of all, an instance of main test will be created. Did you know that good test runners always create an instance of the test class for each execution of each method, of each test method? If you've got 20 tests in your test class, it's going to create 20 instances of that test class. So the very first step is it's going to create an instance of main test, and then it will call setup. And then it will create an instance of subtest 2, and it will call subtests 2's setup. And then it will call the second test method. And then it will call subtest 2's teardown. And then it will call main test's teardown. And then it'll go on to the next test method with a brand new set of instances. And as you can see, if you work that through in your mind, what that's going to allow you to do is move the setups to the appropriate subtests, so that you don't have to do, this big, massive setup for all the tests in the system. It's very nice to have a hierarchical test system, which JUnit now allows, which the other testing frameworks always did allow, more or less. So next time you fire up JUnit, learn about hierarchical testing. And by the way, if you're using something old, if you're using JUnit like JUnit 4 or something, or JUnit 3, you can still get the hierarchical context runner as a plugin, and do a Google search on that and you'll see what that was. Okay, and with that, it is time for, well, there's one thing in the Q&A widget, so let's go answer that question. Let's see, Sarah says, could you use an analogy of using humble object pattern with clean architecture? Okay, humble object with clean architecture. Let me put that diagram back on the screen because I think that would help. I didn't draw it here, but there is an architectural boundary between the data formatter and the driver. And if you'll recall, architectural boundaries require that source code dependencies cross the boundary in one and only one direction towards the higher level component. So that architectural boundary should have the driver depending on the data formatter. From this diagram, you might get the idea that the data formatter has a source code dependency on the driver, but that's not the case. The driver has the source code dependency on the data formatter. What that means is that inside the data formatter, there is an interface that the driver implements. It also means that the data structure belongs to the data formatter. It belongs on the left side of the architectural boundary. It does not belong on the driver side of the architectural boundary. So imagine that architectural boundary separating the driver from the data formatter. Imagine the data structure on the left side of that architectural boundary, and imagine that the source code dependencies are pointing of the driver. The source code dependency of the driver upon the data formatter is pointing to the left, implementing an interface within the data formatter that the data formatter calls, but the driver implements. I hope that answered that question for you. I had to do it in words.
Sorry, I'm having trouble hearing.
Yeah, dumb Siri. Stop talking to me, Siri. All right, everybody. Let's take a quick 10-minute break. If you have questions, type them into the Q&A widget. I will answer any questions that appear there after the break. And then after the break, we're going to get into even more advanced topics like test design. Yeah. All right. Break, everybody. 10 minutes. Let's see, what is it? 10:57. So we'll come back at 11:07. Yeah, well, 7 minutes past the hour. I don't know. It's not 11 for you. All right. See you in about 10 minutes. And we are back, and it's time for test design. I've been promising this one for the last 5 weeks, right? So hold on to your hats, because we're going to talk about how tests ought to be designed. And this is at a slightly higher level. This is not, how to clean a test. This is what the structure of the tests should be. One of the problems that we face with test-driven development, especially for newbies, people who have just started learning how to do test-driven development, is that they will write a lot of tests. They will diligently follow the 3 laws. They will write a lot of tests, and they'll compile, several hundred tests. And then there will be a change to the requirements, which will force them to modify 100 tests. And this is deeply frustrating. You've spent a lot of time on these tests. You put a lot of effort into these tests, and all of a sudden there's a simple change to the requirements that cause 100 tests to break, and you've got to go and touch all 100 of those tests and fix them all. And I have seen it over and over again that new people coming into test-driven development, people who've only been doing it for a month or 2, will just give up at that point and say, well, this doesn't work. My God, I'm not going to go through this again. The issue there is that the tests were not properly designed. And I can prove that point very easily, right? Forget the fact that there are tests in the system. If a simple change to one part of the system causes 100 other things in another part of the system to break, you've got a bad design on your hand. That is the definition of a bad design. That is what bad design means. Touch it in one place and it breaks in 100 other. So the new people who experience that, and by the way, that's called the fragile test problem. It's so pervasive that it's got its own name, right? The fragile test problem. The people who experience the fragile test problem have produced a test design that is suboptimal. How do you design properly? Well, all the same design principles apply. The tests are part of the system. So all the same design principles apply, all the same design principles, everything applies the same way. You have to treat the test code the same way you would treat the production code. But I can get a little more specific than that. I've got a few bullet points here that say, use a testing API to isolate the test from the code. And you might think, well, wait a minute. Why would I want to isolate the test from the code? And the answer to that is, yeah, you do. You want to decouple the tests from the application code. You don't want the tests to be too intimate with the application code. This is one of the reasons that testing a private method is a design flaw, right? Because when you're testing a private method, if you're specifically testing that private method, then you are reaching into a part of the design you shouldn't be able to see. You shouldn't want to see. So I can get a little more detailed than that. The first big problem that I see in the way people write tests, especially when they come into test-driven development for the first time, is that they will write a test class for every production code class. The reason they do this is that most of the books out there tell you to do that. And those books were written at a time before we really understood what the structure of the tests ought to be. But we don't want a one-to-one correspondence between the test classes and the production classes, because of course a one-to-one correspondence is a coupling, a rather intense coupling, right? So when you see that one-to-one correspondence, you should expect also to see the fragile test problem. So then what should the structure be? What should the structure of the tests be as compared to the structure of the production code? And the hint there is that little mantra that I told you about a couple of weeks back, As the tests get more specific, the code gets more generic. Remember I told you about that? I told you to recite that when you go to bed at night and put yourself to sleep by just reciting that mantra over and over again. As the tests get more specific, the code gets more generic. Well, let's look at that. What you're looking at now is just a little hand-drawn diagram. You see the test class to the left. Assume that there's no production code at all yet, and I'm going to walk you through the creation of that production code. So you got a test class there, and the test class begins with nothing in it except the test class, and then maybe one test method. And that test method fails because you don't have any production code at all. So then you create the application class and you add the method, and it still fails, of course. And then you add enough code to make the production method pass. So now you've got a test class with one method in it and an application class with one method in it. And now we want to test something else. So we add another test method. It's going to test the same application method. So now you've got two methods in the test class that are testing one method in the application class. It's just that the application class is doing some other function too, right? There's some different argument getting passed in or something like that. And of course, you add more code to the application method to make this test pass. This continues. Another test gets added, more code gets added to the method. Another test gets added, more code gets added to the application method. And at some point, as you're going around the red-green refactor loop, you realize that the application method is getting ugly. It's too big. So you start to practice extract till you drop. Extract till you drop. Take the clean code course if you want to know what that is. And you start extracting out private methods from the one application method. Well, okay, now you're getting all these private methods accumulating in your class, maybe 2 or 3 or 4, something like that. That's kind of nice. And better structure for the application class, of course. And then you go back and you write more tests. And those tests force you to write more code in the application method. Maybe they force you to write a new application method, a new public method. And you continue to go around and around the red-green refactor loop and extracting out more private methods from the public methods, and the test keeps on getting longer. The test class grows linearly, one test at a time. The test is getting more and more specific. But what's happening to the application class? The application class is accumulating a few public methods and several private methods. And as you go around the red-green refactor loop, you start to realize that there's a lot of code in this application class. There's a lot of private methods, and the private methods are using some of the fields of the application class, but not all of the fields of the application class. And in fact, you could extract out a new class. So you extract out a new class. Your tests know nothing about that class, nothing. Your tests are still going through the public interface of the application class, but you've now taken a whole bunch of those private methods out of the original application class and you've put them in a new class. This continues around and around the red-green refactor loop you go. More and more tests get added to that test class. More and more methods get added to the application class. More and more private methods get extracted. More of those get extracted into other classes. And as you proceed, you build up a family of classes on the right. The original application class becomes the API for that family of classes. It consists of a set of public methods that the test class uses, that everybody else is going to use as well. The whole system will use that application class as its API to this lovely little family of classes. And almost all the classes in that family are private. No one knows they exist, just the application class. If you are familiar with the facade design pattern, that's what we've created here. The application class has become the facade that delegates to all the extracted classes on the right. The test class knows nothing of this. All the test class knows is the public methods of the facade that we've created. The design of these two bits of code are remarkably different. Now, you may be raising your hand and saying, wait a minute, all that extracted code isn't being tested anymore. And yes, it is. All we did was take that code and move it into other places. The tests still tested it. All that code was written to make failing tests pass. Those tests now passing are still testing all of that code. The fact that it exists in private methods in different classes does not matter. It's still being tested. Every line is still being tested. It's just not being tested directly. It's being tested through the API that we have built. This is the fundamental design process that we use with test-driven development. This is how we make sure that the tests are decoupled from the vast majority of the production code. The tests are coupled only to the public methods of special application classes that act as facades to the family of classes behind them. And this greatly reduces the fragile test problem. Not only does it reduce it, it gives you the opportunity in that application class to abstract out the concepts that the family of classes behind the scenes are using. So the application class becomes a kind of abstract presentation of the code behind it in that family of classes. And the tests only know about the abstraction presented by the application class. To the extent that you can pull that off, you can create very decoupled tests, and you will not experience the fragile test problem. So once again, there is that mantra. As the tests get more specific, the code gets more generic. You should now understand that mantra is a lot more important than perhaps you first thought it was, because that is the key to making sure that your tests have the right design. And take a look at this diagram here, because this diagram shows something very interesting, right? The tests, as they grow, they evolve, but they evolve in a direction of specificity. They become ever more specific, ever more concrete, ever more detailed. But the code on the right-hand side diverges completely from that design. That code becomes general and abstract and generic. These two bits of code evolve in diametrically opposed directions. I bet you didn't think that was true. That is the topic of test design. As you practice test-driven development, start to feel this out. Start to feel out how the tests get more and more specific, but you can manipulate the production code to be more and more generic. Don't fall into the trap of letting the production code look like the test code. In the worst case, if you make the production code look like the test code, in the very worst case, you will have an if statement in the production code for every test method in your test class. If I'm executing test 1, then the answer is this. If I'm executing test 2, then the answer is this. That's the extreme case of the production code becoming more and more specific instead of becoming more and more generic. Clearly, we don't want to write the production code that way. We want to grow the production code in a general way as the tests grow in a specific way. Looks like Francesco put something in the Q&A widget. I neglected to answer that when I started the lecture, so I'll answer that now, Francesco. You haven't written Java for a while, so what's the relationship between the test classes in a testing hierarchy? Are they inner classes, subclasses? Well, they're inner classes. Yeah, in every case that I know of, the tests in the deeper parts of the test hierarchy are inner classes of the main test class. That's in test frameworks that are written in an object-oriented language. There are other languages that are not necessarily object-oriented or not primarily object-oriented, and they use an equivalent kind of data structure, a data structure that is nested within the data structure that holds the main tests. So you can have this recursively defined data structure that holds the tests and holds the setups and holds the teardowns. And it, of course, can contain another data structure of that kind. And so you have this, recursive descent of tests in a hierarchical fashion. So most languages, it's done with inner classes. Some languages, they use recursively defined data structures. All right, now on to more mundane topics. A couple more to cover, still important. So for example, I mentioned the humble object pattern. That's just one aspect of testing GUIs, but there are several other things that we should talk about. First of all, testing GUIs is hard, and the reason it's hard is the reason I've explained already. As you pass outside the physical boundary, it starts to get pretty impractical. So I use humble objects to do that, and I verify my GUIs by eye. I do manual testing. Yes, I do manual testing of my GUIs, but I do it in a special way. I do it in a way that allows me to continue the red-green refactor loop without an automated test, but still just as fast. So if I can get my code up on the screen, like my CSS code on the screen or my GUI code on the screen, and I can paint the screen in some very quick way. So I will write special little bits of software that'll paint the screen without going through the whole navigation structure and without going through the whole, business rule structure. I will paint the screen, and then I will look at the screen and fiddle with it until it looks right. And that fiddling is still going around the red-green refactor loop. It's just that red now does not mean that an automated test feed fails. It means that my eyeball test failed. It doesn't look right. And then I make it green, then I clean it up, and then I continue around that loop with my eye. And hopefully I don't spend too much time on that because I don't want an awful lot of untested code. I recently wrote a space war program in Clojure. If you look at the cleancoders.com website, you'll find in the functional programming section of that site, you'll find a bunch of videos where I introduced this space war program written in Clojure. And the GUI was very dynamic. I got spaceships moving across the screen, and I've got phasers firing and torpedoes firing and explosions, and it's all very nice, right? Very, very, very pleasant. And all of that GUI stuff, I had to do by eyeball. I want the explosion to look right. Well, okay. So I come up with some algorithm for an explosion, and I try it on the screen, and it didn't look right, and try a few other things. And then eventually I get it to look right. There's no tests around that. I couldn't write any tests around that because I didn't know what the right answer was until I finally saw it. And so that does happen. However, very often, having said all of that, very often, it is still useful to test GUIs. Some of you may have purchased a GUI tester. This is a separate system that pretends to be a human and interacts with your system through the human interface, right? So, or something very close to the human interface. It doesn't actually, hit the keys on a keyboard, but it sends the right messages to your system that makes your system think that keys have been pressed on the keyboard or that mouse clicks have happened, things like that. There's a number of systems like this, and many people will use them to test their GUIs. So if you have one of those, and a lot of people do, Don't do this. This is terrible. This is a horrible design flaw, right? Do not test your business rules using the GUI tester. Do not test business rules through the GUI at all, right? Don't, and why not? Because the GUI is designed to be volatile. We want the GUI to be able to change. We want the marketing people to be able to say, I don't like the way that looks. I want it to be a different look and feel. And you don't want that to break all of your tests. When the marketing people come up with a new navigation structure, you don't want all your tests to break. So don't test through the GUI. Don't test your business rules through the GUI. When you're testing your business rules, make sure you've got a business rule API that you can test your business rules directly with. And don't even couple the GUI to it. When you're running these tests, don't fire up the web server. Don't let the GUI be running. No screen should have HTML on them at all. Just write nice tests that call right into the application, bypassing the GUI altogether, so that you can test your business rules without the GUI being there. Can you imagine, how awful it is to test a business rule by having to first go to the login page and log in, and then navigating down to the purchase page, and then trying to fill out a purchase that's valid, and then clicking the buy button, and then looking at the screen to see if, can you imagine how awful that would be to do that, and how long it would take? Where, if you test right through the business rule API, those tests would take milliseconds, and they'd be very easy to write, and they wouldn't be dependent at all on the navigation structure of the GUI and so on. Write yourself an application API, which, by the way, the GUI will use. The GUI will use that API to do all the things it wants to do. You're going to want to use tests for that as well. Tests will use that same application GUI. Now, what about the GUI? Let's say we want to also test the GUI with one of these automated GUI testers. Well, fine, you can do that, but you don't have to have the business rules plugged in. In fact, it's much better if you don't have the business rules plugged in. Replace the business rules with a stub, and then test the GUI with your little GUI tester, whatever that might be Selenium. Selenium does that. That's one of the tools. There's a bunch of others. Robot FX, I think, is one of those tools that used to do that. There's a whole ton of these GUI testing tools. Fine. Decouple the GUI from the business rules, replace the business rules with a stub, so that the tests you're using are not testing any business rules. The tests are just testing the GUI. They can test the navigation structure. They can test the way things look on the screen. Maybe you can even get them to test a little interesting drag and drop stuff, but don't let them test any business rules. And that leads us to a topic that I've completely avoided until now, which is, what the heck other tests are there? We've been talking about unit tests for the last 5 weeks. Now we're going to talk about different levels of testing. I'm not going to spend a lot of time on this, but I do want you to be aware that other kinds of tests are necessary. This is related to Mike Cohn's wonderful pyramid of testing. It's a little bit different than the way Mike draws it, but the intent is the same. I tend to make mine a little more technical because I'm a programmer, right? So most of the tests we write are going to be unit tests. And you can see down there to the left, I say that's approximately 100% coverage, right? That's the goal. The goal for unit tests is to get as close to 100% test coverage as you can get, right? 100% of the lines, 100% of the branches. No, you can't do 100% of the paths. Nobody can do 100% of the paths. Don't go down that alley. But you can do very close to 100% of the lines and branches. On the right, you see it says X unit there. All I'm saying there is that these are tests written in a programming language, generally the same language that the system is written in. using a testing framework of some kind, like JUnit or NUnit or RSpec or Jasmine or something like that, whatever your testing framework is. Unit tests are tests written by programmers for programmers. The authors are programmers, the audience are programmers, right? Nobody else has to look at them. These are the tests that programmers use to prove to themselves that the system does what the system is supposed to do. One level up are the component level tests. Some people will call these acceptance tests. Some people call them customer tests. It's always this, it's the same kind of test. These tests are written by QA and by business analysts. That's the ideal. That's, we want them to be writing these tests. These tests test business rules. They don't test all of the gunk that the programmers need to test. The programmers have got to get in there and test all the exception cases and all the weirdo pathways that go through the code. These component tests don't test that at all, right? They're just testing business rules. They're written by generally business people, QA people, business analysts. They're usually written in a language that is slightly higher level, some kind of table-driven language that looks like a spreadsheet. That's very common. Fitness or SpecFlow or JBehave or Cucumber, tests that are meant for non-programmers to read and write. That's what I mean by API down there at the right. They're written against an API tester, something that can test at an API level. Unit tests test a lot below that, but component level tests test at the business rule API level. The amount of coverage you're going to get is going to be less than 50%, because there's a ton of code that you cannot reach from the business rule interface. If you are sitting at the keyboard typing in, trying to get at business rules, there's a whole bunch of code in the system you can't get. You can't get all the error handling code. You can't get at the code that deals with the fact that the network went down, stuff like that. So the component level tests have the same kind of limitations. They're not going to test all the horrible code down there. They will test the business rules. And 100% of the business rules, just not all that other code. Those two levels are your continuous build. When you have a continuous build in place and you run it, you will build, then you will run all the unit tests, then you will run all the component level tests. And the build will pass if those tests all pass. Typically, the remaining tests in the pyramid are not done during the continuous build. I say typically because there are exceptions to that, but the reason that they're not done as part of the continuous build is that these tests start to get slow and difficult. So the next level up are the integration tests. Integration tests are tests, first of all, they don't test any business rules. Integration tests test the data flows and the execution pathways through large swaths of the system. These tests have wide scopes. This is the kind of test where you would be firing up separate JVMs and you would be talking through sockets. It may not be, these tests may not go through the whole system, but they go through large pathways of the system. These tests tend to be written by architects and lead developers, people who really understand the high-level structure of the system. Again, they should not be business rule tests. I mean, you'll have to pick a couple of business rules to test in there, but testing a business rule in this context is just a crutch so that you can test the information flows. The real goal of these tests is testing the information flows and the choreography of the execution pathways. I say they're 20% coverage. That's actually very optimistic. I doubt you'll ever get 20% coverage here. Again, these are plumbing tests, tests of the plumbing of the system and the dynamic choreography of the system. They're not business rule tests. The ultimate integration test is the system test. This is when you actually put the whole thing together and you test the entire system. And in the most extreme case, you're going to use a GUI tester for that. You're going to fire up some GUI tester and then just hammer on the system that way. Once again, these are not business rule tests. You do not need to test every business rule with a system test. Once again, this is just the ultimate integration test. It's a plumbing test. It's a choreography test. These two bands of tests, the integration tests and the system tests, tend to execute longer. The system tests especially execute longer because they're going through the GUI. So you've got to have the whole GUI system set up, the whole web server, if you're using a web server set up. You've got to have all this stuff set up. You've got to have a GUI tester, which by definition is slow. So these tests will take a very long time. Integration tests also take a long time, although they can run a little faster. But they take a long time because you're probably starting up multiple processes and you've got timeouts and delays, and there's all kinds of, multi-threading and multi-process stuff going on. So you can expect integration tests to be many times slower than the component tests. You can expect the system tests to be many times slower than the integration tests. But the reason this triangle narrows as it goes upwards is because there are fewer and fewer of these tests as you go up that pyramid. There's a lot of unit tests. In a good sized system, there will be many thousands of unit tests, maybe tens of thousands of unit tests. There will be many hundreds of component level tests. There will be many dozens of integration level tests. There will be 1 or 2 or 3 system tests, maybe 5. Though that's the level, right? So as we're going upwards, the number of tests decrease, but the time required to execute those tests increases, and the time actually wins. Right. So typically, you should be able to get all the unit tests executed. Even if you've got 10,000 unit tests, you should be able to get all of them executed in a couple of minutes. 2-3 minutes, something like that. I worked on one system where it actually grew to 4 minutes. I thought, well, that's absurd. And I went in and I had to do a redesign just to get it down to 1 minute, right? So that's the kind of level that we're talking about. Unit tests should run fast. Component level tests, well, they should run almost as fast as the unit tests. Each individual test will take a little bit longer, but there are fewer of them, and so the amount of time is roughly comparable. That's why those two can sit in the continuous build. The rest of them, they can't sit in the continuous build, generally speaking, although, there are special cases where maybe you can get the integration tests into the continuous build. But in the general case, the integration tests and the system tests are specially run. They are run maybe once a night or once a week. They may require a special bit of hardware or maybe special time reserved on the network. There's constraints that the integration and the system tests must operate within. And then finally, the last batch of tests up at the top, those are exploratory tests. These are manual. These are manual tests, but they are not scripted manual tests. I don't want any scripted manual tests. I don't want you to open up a book that says, okay, now type this and hit X. I don't want that kind of thing. Exploratory tests are very creative. And typically you hire experts for this. There are people who are experts at exploring other systems. I have walked through airports with some of these experts, and it's fascinating to watch what they can do to a ticket machine. But never mind that. Exploratory tests are tests that you might run once every 6 months, once every year. The goal of those tests is to get the experts, whoever they are, and ask them to find ways to break the system. To just go in with as creative an amount of effort as possible, find holes, find ways to break this system, go in and really mess with it. I worked for a company once that did a kind of exploratory testing. They didn't hire experts for it, but it was still very effective. Once every 3 months or so, they would declare a day of bug hunting. And they literally got everyone in the company to stop whatever they were doing. And for one day, everyone in the company, secretaries, janitors, didn't matter, would bang on the system randomly, just trying this, trying that, find some way to break it. And the company would give awards to the people who found the most interesting bug, or the bug with the most steps in it, or the bug that did the most terrible crash, you know, that kind of thing. You get a dinner for two, you know, that kind of an award, little cash awards or little coupons from, you know, Outback or Olive Garden or something like that. So that's another strategy. If you've attended any of my talks at any time, you've probably seen this picture come up on the screen, but I will just say it again. The hands that you are seeing here are the QA manager. The document that man is holding out to me is the table of contents for the manual test plan. It is not the manual test plan, it is just the table of contents. He had 80,000 manual tests that he needed to run every 6 months. It cost him $1 million. I just talked to a guy yesterday who had the exact same problem. And in this case, this was in the year 2008. He's holding this out to me because he says, I got a hell of a problem. My budget's just been cut by 50%, you know, financial crisis of 2008. My budget's just been cut by 50%. Which half of these tests should I not run? And, you know, the answer is, well, you know, you can cut the document horizontally, vertically, or depth-wise. You're not going to know if half your system works. That is the dilemma of manual testing. That is why we talk about this automated testing pyramid. We don't want to do manual testing for the first 4 levels there, because we don't ever want to be caught in this trap where the accountants finally tell us that we can't run our tests. Manual tests are always horrifically expensive. These automated tests are not. They're expensive to write. They are not expensive to run. Manual tests are expensive to write, and they're even more expensive to run. Why in the world would we ever do manual testing? We're programmers. We automate things. Why would we ever do manual testing? Yes, I should talk a little bit about legacy code, and maybe we've got a little bit of time to talk about behavior-driven development, although that's a very short discussion. In fact, let's do that one first. Let's do the behavior-driven development discussion first, then we'll do the legacy code discussion. Both of them are quick and will be done in time. Behavior-driven development, people will always ask me, well, what's the difference between behavior-driven development and test-driven development? So behavior-driven development was invented as a derivative of test-driven development. Dan North, lovely fella who lives in England, was doing test-driven development one day in the early 2000s, and he didn't like the way the tests read. They were too techy. And he came up, with the help of some other people, he came up with a new vocabulary, which I'm sure you've heard of, given, when, then, you know, the given, when, then vocabulary. And he built a tool called JBehave that allowed him to write tests using this vocabulary. Now that's behavior-driven development right there. It's just stating your tests using a different vocabulary. Now let me do the analysis here because it's pretty interesting. I told you that tests are composed of 3 elements: arrange, act, assert, right? Arrange, act, assert. Well, given, when, then are synonyms for arrange, act, assert. Given that I have arranged the system, when I act on the system, then I will assert the results. I mean, very clearly, those are synonymous ideas. Dan North just liked the way it read better. And I can't disagree with that. It does read a little bit better. And when I am doing acceptance level testing, component level testing, the second level in that pyramid, I will typically use the given, when, then vocabulary. Even if I'm writing unit tests, I like to use the when, then vocabulary. I don't like the 3 components. The 2 components, I think, are fine for unit testing. Now, before I get into the state machine analysis analogy, let me say this. The vocabulary was so evocative that quite a few people entered into the behavior-driven development school of thought, and they started to divorce themselves from automated tests. And the reason they did that is that they realized that the vocabulary was a good vocabulary for writing functional specifications. And they started focusing on the idea of teaching and consulting the way to write functional specifications using behavior-driven development vocabulary. And they came to the conclusion that even if you didn't write tests, using that vocabulary to write functional specifications was valuable. Now, I can't argue with that. I think that's fine. Although I think you're missing a heck of a bet if you don't write the test, for God's sake. I mean, we definitely want those tests to be automated, but I understand the point that you do get some benefit when you're writing a functional specification. Okay, fine. So there's a little philosophical battle going on there, which you probably don't need to know about, other than to say that the BDD folks have tentatively or tenuously divorced themselves from the absolute need for tests. They don't mind if you run tests. They just kind of said, well, we're going to go ahead and do this even if you don't run tests. And on the test-driven development side, we're still kind of like, well, yeah, but you got to run the tests. You got to have tests. The last thing I want to say about that is just a little quirky thing about given, when, then, or arrange, act, assert, and finite state machines. Anybody who studied finite state machines knows that the transition of a finite state machine can be described in this way. When the system is in a given state, or let me start over. Given that the system is in a certain state, when I get a certain event, then I go to the next state. Given that I am in the locked state, when I twist the key in the lock, then I am in the unlocked state. Every finite state machine ever written can be written as a sequence of given, when, then statements. That's called a state transition table. State transition table is a sequence of given, when, then statements, which means that every suite of tests ever written, they all follow the given, when, then formula, or they follow the arrange, act, assert formula, which is synonymous. Every suite of tests ever written is a finite state machine. It is the finite state machine of the system being tested. So when you are writing a suite of tests against production code, you are writing the finite state machine that describes the behavior of that system you are testing. And I want you to think about that one. Go to bed at night and use that as fodder for your dreams and see what you come up with, because that's just an interesting little quirk. Okay, last topic. Legacy code, legacy code. And then we're going to end. This is the problem that everybody has. Maybe I should have made this the very first thing we covered, because everybody has this problem. All of us out there are working on a current system that is ugly and has no tests. And the question is, well, what do you do? How do you operate? When you've got this horrible, massive legacy code with no tests, what do you do? Should you start a project to get it tested? And the answer to that is no. Do not start a project to get it tested. Do not go to your boss and beg for time. Do not go to your management and say, we need 3 months, give us 3 months and we're going to write tests and life will be beautiful after that. Don't do that. And don't do that because A, it'll take a lot more than 3 months, and B, you will fail. And the failure will be spectacular, and you will lose credibility, and no one will ever let you do anything like that again. What it's going to take to deal with legacy code is a shift in attitude. Now, if you want to know what that shift in attitude is, get this book and read it. Working Effectively with Legacy Code. Wonderful book. Also the most depressing book you will probably ever read, because it makes it very clear that there's no quick solution to this. But it is a book full of very good techniques and very good attitudes. I strongly recommend it. However, quick summary. How are you going to get out of the mess? You get out of the mess by shifting attitude. Everybody on the team has to adopt a new attitude. You can't have any stragglers. You can't have one guy who doesn't follow the rules, because that guy will wreck it for everybody else. Everybody has to follow the rule, and the rule is the Boy Scout rule. Every time you check the code in, you check it in a little cleaner than when you checked it out. Every single time. You never check it in worse. You always check it in better. Just before you check it in, you do some random act of kindness to make the code a little better. In the early days, this probably will not involve writing tests because the system is difficult to test. It was not designed to be testable. There are couplings that prevent you from actually testing the system in any kind of practical way. So you'll have to do other random acts of kindness, just simple things that make it a little more readable, a little less coupled. Over time, these little improvements will accumulate, and at some point you're gonna bring up a module, and you're gonna realize that it's clean enough to write a test. Write a test, check it in. Don't write 80 tests. Write a test, check it in. When you're doing these random acts of kindness and then eventually little random tests, do them in a low risk way, because the risk right now is very high. The risk of changing that code is very high, and you don't want to fall into the trap of breaking it and then owning it for the rest of your life. As time goes by, things will get gradually better and better. The code that you are touching will get cleaner and cleaner. Some of the code you are touching will even start to accumulate some tests. The more tests you accumulate, the better it gets. However, there's a whole bunch of code in that system that you are not touching. You're being asked to add new features. You're being asked to fix bugs. You're going to be touching the more volatile parts of the code. But there are parts of the code that nobody's touched for decades. Well, maybe that's an exaggeration. Years, right? And don't go into that code and muck around with it. Don't go into that code and try and clean it. Leave it alone, right? Gradually make the code you are forced to deal with better. And this will separate your system into the volatile code that is getting better and better, and the stable code that is not getting better and better, but you don't care because you know it works. Perhaps sometime in the distant future, you will have improved enough code in the system, enough of that volatile code, and you find that you have completely surrounded some chunk of the old system, some stable chunk of the old system. You've completely surrounded it with new and better code. You may at that point decide that you could rewrite that little bit that you've surrounded. Don't rewrite big chunks, but maybe you could rewrite a little chunk of what you've surrounded, rewrite it with test-driven development, make it better. One last point. Sometimes you will be asked to add a new feature, and you will realize that there's two ways that you can add this new feature. One way would be to smear it through the body of the code, as we always have done, making the mess worse. And the other way would be to implement the new feature in an entirely separate module that you must couple into the legacy system, but that still remains isolated. That strategy will take longer. Do that strategy anyway and write that module using test-driven development. because you don't want to make the problem worse. Everything you do to this system, you want to make the problem better. And with that, ladies and gentlemen, we are done. There is a question in the Q&A widget. Sarah asks, as we get more generic in production code, our test setups become bigger, right? Well, not if you're doing hierarchical testing. We would have to create all the dependencies for the code we're testing. Not if you're doing hierarchical testing. I mean, you still do have to create all those dependencies, but you can isolate them down into the hierarchy of the test. And those dependencies would be the real dependencies, not mocks. Well, now, if you're crossing an architectural boundary, I think we would want to be using mocks. If you're not crossing an architectural boundary, I talked about this before, right? This was the TDD uncertainty principle. If you're not crossing an architectural boundary, then yes, you're right. You're going to be accumulating dependencies within the architectural element you are within. That is not too painful. What I don't want is for those dependencies to go transitively across into other architectural elements. And by the way, when I'm talking about architectural elements, these architectural elements are generally smallish chunks of code, not, massive 10,000 line things. They're usually less than 1,000 lines of code, little architectural elements across which we control all of our dependencies. Single use cases, single entities, single controllers and presenters, that kind of thing. So you're right, Sarah, if you follow my strategy for the TDD uncertainty principle. Within an architectural element, yes, some of these dependencies will accumulate. You can manage that nicely with hierarchical tests, but the dependencies still do accumulate, and you're not going to be using as many mocks. Across architectural boundaries, you'll be using the mocks, and so that's the way you escape from that at scale. All right, so that's that question. And now Francesco has a question. You said component tests are written by non-programmers. Yes, well, that is the ideal. It does not necessarily work out that way in every case. You continue, but they need to be automated. Should the test writers use a predefined set of small steps in order to compose a very long test, which ends up being awful to read? No, they shouldn't do that. Or should they define very specific steps in order to keep the test small? Yes, they should do that, of course. Typically, I like to isolate the test by business rule and by business rule case. So there's case 1 of the business rule, case 2 of the business rule, case 3 of the business rule. Each one of those would have its own relatively small test. You're going to build up a test suite of all of the business rule cases. Now, who's writing this? I want the QA and business analyst people writing these tests. Are the programmers involved? Yes, of course. Programmers are involved because the programmers are the experts on how to isolate things. That's one of the big jobs of a programmer. How do we properly isolate things? So yes, the programmers will be involved in that, but not at an authoring level. We still want the business rule, the business analysts and QA people writing these tests with advice from the programmers. Can you get the business analysts and QA people to write these tests? I've worked on projects where we have, and it's a wonderful thing because the business analysts and the QA people define the system. They define the requirements of the system in terms of tests. And then the programmer's job is to make those tests pass. That's how we get the system properly defined. However, it is much more common for the business analysts and QA people to not want to write those tests because they don't think they're programmers and they don't want to get into some kind of formal specification. And that's a problem. I've had it where a business analyst says, well, you want me to write the code for you too? And so, there's an attitude issue here. There is a need for we on the development side to convince the folks on the business side that they do actually have to focus on some details. They're not going to be able to specify the system if they don't focus on details, but it's a hard sell. So what we do then is we programmers may write these tests in a nice language that the business people can read. If the business people will at least read these tests, then I say it's worth it to write them in Fitness or JBehave or some kind, or Cucumber, or some kind of high-level language like that. Because then you get the business people at least involved, and they can look at those tests and go, yeah, that's the way it should work, or no, that's not the way it should work. If the business people refuse to even read, after a good college try, you've tried to sell them on it, they won't even do any of the reading. If the business people refuse to even read the tests, should these tests be written? And the answer to that is yes, these tests still need to be written. We need to have tests at the component level, at the business rule level, that describe how the system behaves at that level. Unit tests are not sufficient. Unit tests may cover everything, but unit tests don't test business flow. So yeah, these tests do have to get written, and you're going to have to, programmers are going to have to write them, but there's no reason to write them in some other language, right? You don't have to get SpecFlow or JBehave or Cucumber or something like that. If the business people aren't going to read them, you don't need to go through the pain of integrating with that kind of a framework. Just write them in, whatever language you're using. Use the same technique you use for doing unit tests, just make them wider scope tests. And then, hope one day you can convince your business people that they actually do need to participate in the specification of the system. Okay, and that seems to be the last question in the Q&A widget. So thank you, everybody. I hope you enjoyed the last 5 weeks. I hope you learned an awful lot. This is always fun for me. And I assume it's fun for Angela too, even though she sits here and listens and she's heard it all before. I've heard it all before too. Anyway, thank you all for attending, and we'll see you on another course. Perhaps you're all going to come to Clean Agile, right? That'll be a 2-week course where I rant and rave about what's happened to Agile and what Agile really should be. Bye, everybody. I'll turn it over to Angela.
Oh, did you hear that?
Go ahead and mute yours. You do love that. And you have to turn off your volume. All right. Oh, nope.
Oh, I hit the wrong button. Where's my, oh, there it is. There it is.
Okay, he really does enjoy doing that. Thanks for your patience while we fixed our sound here. Thank you all for participating for the last 5 weeks. As Bob said, we hope that you enjoyed it. He and I both enjoy doing this a lot. It brings us together every week, which is awesome. Our next course is Clean Agile, as he mentioned. It's beginning October 13th. You can find out more information about that on Eventbrite at the Clean Coder. And as always, you can email me if you have any questions or any issues with this course. We would love some feedback. So please feel free to send us some feedback if you have any. Angela at Clean Coder is my email address. The recording for this event today, this webinar, will be in Dropbox within the next, well, by tomorrow. It will be there for sure. So that concludes this course. Thank you all for participating. We hope to see you in a few weeks, and that's it.
Bye.
See ya. Bye, everyone.